Good evening and welcome everybody. This is Obi-Wan Pez for N Simplex Pachinko. We are working tonight on anything that anybody wants to work on. So tonight we've got final exams are in full swing, at least at my school. I don't know about anybody else, but yeah, got students all in a panic. I hesitate to say it's great, but in some ways it's rather amusing. In others, it's kind of sad. So if anyone has any particular questions they want to talk about, otherwise we can just do some other rant. That's not black. Oh dear. There we go. Anyway, yes, so I was also really impressed just a couple minutes ago when I found out that my time was incorrect on my soon screen. So the time stated EDT instead of EST because we are switching now to Eastern Standard rather than Eastern Daylight in the United States. And so I needed to switch that. I thought I was going to not be able to edit the card. Silly me. Apparently it allows, like, OBS apparently does not constantly read or have the card open. It's just calling it, and basically if there's a change, it'll recall. It'll detect whether there's a change to the card and then recall it. So that's pretty awesome. At least in that way I don't have to like exit out of it and then save and exit and then change it in OBS and then update it again in the have OBS closed and then save and upload, because that would be kind of annoying. So I hope everybody's been having a good week. Like I said, the final exams at my school are in full swing, where I just had all four of my classes exams today. I had to proctor 3 of them. And I've been getting a lot of emails about whether or not I can still accept assignments. Like, no. I told you I was not accepting assignments after Tuesday, so... Everybody's nervous about their grade. I'm like, dude, if you know what you're doing, you have nothing to worry about. And if you don't know what you're doing, there seems to be a bigger problem than what your grade is. Okay. So, we'll just leave it there for now. My chair has a slow leak in it. I keep occasionally feeling it kind of sink down another couple of inches. Occasionally have to pop back up again. Oh, man. And yes, I'm sure that someday some chair company's going to be like, hey, Obi. But today is not that day because I only have like 5 viewers, so ever. I have very much appreciate the people who are coming still on video on demand and all that. So thank you everybody for stopping in and at your leisure. I hope you all are having a good time and learning a bit of math. That's also an interesting thing here. That's off by a factor of 4, and then we do a 3m plus 1 on these. Or m minus 1 over 3 on each of these. And then we double twice here, and we get almost the same number. Oops. No, we're not doing it anymore? Okay, there we go. Well, as I've said in the past, this is kind of my almost like mandala work here, or adult coloring books. Not that kind of adult. Anyway, yeah, so this is kind of like my coloring book sort of habit here, just going through and placing numbers down, trying to make them show more interesting patterns as we go through the Collatz space that's here. There was a little while where I thought I might have something, but unfortunately I don't think so. Pretty sure it's just a pipe dream. But playing in Collatz space is very interesting nonetheless. And then you can also take other Collatz spaces or other patterns that are similar to Collatz. So like I said, you know, anytime you start with a number, if it is an even number, you just keep dividing by 2 until you can't do it anymore, i.e. it turns odd. And when it's an odd number, you triple it and add 1. So 5 becomes 16, triple 5 becomes 15, plus 1 is 16. And then 16 is even, which is guaranteed after every tripling and then adding 1. It's always going to switch to an even, and then you just divide by 2 until you can't anymore. And eventually, the Collatz conjecture says, you'll get 1. Now, every single number has been tested a long way out in pretty much every direction with a bunch of mathematicians doing computer work. So they've gotten like every single number up to several million / billion / who knows, all mapped out. But I don't know. I think I'd like somehow I think I'd like a 3D representation of it. I have seen somebody had a something that looked like a coral reef, basically built out of Collatz space numbers, and it was very beautiful. It is art in its own right. Just wish I could code that kind of stuff. So can eventually, maybe. Not today. All right. So moving on to serious math. If anyone wishes to put out a request, please let me know. And I have not worked out a queuing system on Stream Elements yet. I'm starting to get into doing all of the like variables and things like that. So we're getting there. For right now, though. that. Cool. Okay. Anyway, enough of me playing around. So, if we want to get into some other cool stuff that we found, I'm going to take a question off of this thing here. So one of the things that we do in my math literacy class is logic. And so oftentimes we'll do work with logical statements and try to prove the logical consistency of particular arguments and that sort of stuff. So thought I'll throw this out while we're waiting for other people to gather, or okay. So in terms of logic, we have something that's similar to statement P implies Q and not R. Or R and P. So I'm just kind of making this up at this point. But this is something I might find interesting, so we'll see if this is logically equivalent to something super easy like P. Or if this has any other implications. Okay. So when we're looking at stuff like this, we would want to create a logic diagram or logic table for it. Typically, my students are asked to say, okay, we've got P, we've got Q, and we've got R as our basic variables, or the basic statements that we're going to be testing. We have 8 possibilities for truth and falsehood for each of these things. So we're going to go true, 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 true. False, 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 false. With every bit of this represented. So Q is then going to be true, true, false, false, true, true, false, false, where R is equal to true, false, true, false, true, false, true, false. Now, these could be in any order, but these are the simplest orders that you can get. So P is going to have two different sections. One's true, one's false. Q is going to be broken up into 4 different sections of truth and false, true and false. R is going to be broken up into 8. So it's oscillating back and forth between true and false. So now what we'd want to do is break this down into like all of its individual pieces and say here what we can do is do like Q and not R. But for my students, usually we say, okay, if you've got R, you might as well write not R as well, just so you're not going to accidentally mess it up. So we can go false, true, false, true, false, true, false, true. We're going to have Q and not R here. So again, with these particular students, especially this is math for liberal arts majors, right? So we want to give them opportunity to or fewest opportunities to make mistakes as possible. So individually look at, okay, now take the bigger part of it. What is Q and not R? Okay, in the case of Q and not R up top, we've got true and false. So and statements require both pieces to be true in order for them to be true. True and false is going to be false. True and true is going to be true. false and false is false. False and true is false. True and false is false. True and true is true. False and false is false. False and true is false. Okay, now we'll take the implication that P implies, parentheses, Q and not R. All right, and in this particular case, P implying Q and not R is going to be, right, just as a reminder, for any, let's not do P and Q, let's do A implies B. For any A, B, A implies B. Right, we'd be saying if this is truly an implication, if the statements are true, then the implication is going to be true, at least in logic. It will be a logically valid argument. If we have the the statement in the front is true, implying something that's false, then the implication is false. Right? If it snows tomorrow, then we have school. In that particular case, A being true is it will snow tomorrow, and B being true would be we have school. So if we end up having school and it snows, then the statement, if it snows, then we have school, will be true. I don't like using the one in the negative, even though it makes more sense realistically. All right, so the weather forecast ended up being super light, but then the snow comes in and just barrels through the entire area. If it snows tomorrow, then we have school ends up being a false statement here for our implication. So if it snows tomorrow, then we have school. Well, we didn't have school. So the implication, if it snows tomorrow, then we'll have school, was false. And then if the weather report was wrong and the snow just blew right past us and never actually touched us, here, if it snows tomorrow, right, it snows tomorrow is false. So then we can't actually test the truth of this implication. It could still be true that if it snowed tomorrow, then we would have school or not have school. But if it doesn't snow, then we can't test it. So these are going to leave the implication as true. So here, the only implication that we're going to have that leads to a false statement is if we have a true initial statement and then the final statement, conclusion, is going to be false. So true implies false is false. Everything else is true for implications. So here, P implies, parentheses, Q and not R. We're going to look at, again, P, first column, and Q and not R, this last column here. So we have a true statement P implying a false statement Q and not R. So we just talked about that. That's going to lead to a false implication. True implies true is going to be true. True implies false is going to be false. True implies false is going to be false. False implies anything will be true. Because again, the implication is going to be true because we can't disprove it. So we end up with all these true statements at the bottom because P was false. So the implication could still be true. We just don't know. All right, last section, R and P. So both R and P need to be true for this to be true. We have here true, true is true. True, oops, false is going to be false. True, true is true. True, false is false. All right, and then for all the rest of it, it is going to be true due to the fact that, again, our initial statement P is false. So the implication will still be... That's not what I'm looking at. That's the wrong one. Very sorry. No, I am wrong. Sit there in my wrongness. All right. So R and P, for all the bottom ones, we have P is false. So R and P is going to also be false. It's not possible. Okay. And now that we have the last two statements here, we have an or between them. So parentheses P implies parentheses Q and not R, or R and P. So we're going to take these last two things, and then we're going to or those two statements, take the union of them. So here, if either of them are true, the overall statement is going to be true. So false or true is true. True or false is true. False or true is true. False or false is false. True or false for all four of the bottom ones is going to be true. True, 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 true. So the only one of these that is going to yield a false statement at the end is when P is true, Q is false, and R is false. So in that particular combination, that's the only way that this last statement can be false. For every other outcome, this will be true. All right, sometimes with our logical statements, we also used the slightly more philosophical format. So this is the kind of thing that I learned in like Philosophy 101, where we're saying like P let's just go with it snows. Q so in the case of P is it snows, Q is we have school. The particular statement that we were talking about before, like you can make a logical argumentation. And put down something like if it snows tomorrow, then we will not have school. And yes, I am negating this on purpose, so. Right? If it snows tomorrow, then we will not have school. We have school, therefore it did not snow. So using the time frame words and stuff like that can be additive. You're allowed to do stuff like that, and because it's basically like you're just adding a new little piece of information to it. We're not changing the statements themselves or their truth or falsehood by adding a little bit of a caveat to say, well, we're talking about tomorrow. And also similarly with verb tenses. As long as you're agreeing with how this is supposed to work. So here, the symbolic form is supposed to take the sorry. The symbolic form is supposed to take sort of a similar form as the way that this all works in philosophy class. So when I did it, it was, if it snows tomorrow, then we will not have school. Then on the next line, we split this statement into two different pieces. So the conclusion goes all the way at the bottom, and basically what we're doing is we're like sort of adding the two statements above in order to get the one below. It's almost like a mathematical addition problem or something like that, but ish. So for this, the symbolic form is if it snows tomorrow, then we will not have school. Says that we're going to start with P, and we're going to imply we have school. Well, we will not have school. So this is going to be P implies not Q. And then the line underneath it, we say, okay, we have school. So in this case, we have school is the statement Q. And then you put a line underneath it and say, therefore, using the 3 dots notation. So therefore, it did not snow, so not P. So if we do this using the logical argumentation that we had talked about, and you could use a truth table to figure out all the possibilities here. This is going to get us this, and then we have to state whether this is a valid argument. There we go. Sorry, I was getting my terminologies backwards. I was like sound, but no, that's something else. So is this argumentation here a valid statement? And so the answer is yes, because this here, basically, it doesn't exactly, but it takes the form of Q implies not P. Now it technically isn't Q implies not P because we're not saying if, then. We're making a statement in this case. Q is a fact. So Q, we have school, is a fact. Then not P is what we're stating should be the deduction, the conclusion that we get from having P be true, and also in assuming the implication up at the top is a true implication. So does P implies not Q also be equivalent to, is it equivalent to, Q implies not P? Which again, not exactly, but it's close enough to that statement that we don't have to split hairs too much. And the answer here is yes, these are the same thing. So these are logically equivalent to each other. They are contrapositives of one another. So if you remember, the contrapositive is that you negate them and you also take their inverse on those statements. So you reverse the implication and negate both pieces. Okay, it's not the inverse, sorry. The inverse is when you negate things. Sorry, you take the converse by switching the positions of these things, by switching the implication. So not Q implies P is the converse, and then we invert that statement to make it Q implies not P. And again, those are contrapositive, so they are logically equivalent to one another. And then if we went through the truth table, we could also see that that's true by saying, okay, P and Q are like these here. I'll just do it over again. That's fine. Right. P. Oh no. Let's do not Q. Could probably pick two letters that are not so close together when you look at them. P implies not Q. And then we also want not P. And Q implies not P. All right, so true, true, false, false, true, false, true, false. Not Q is going to be false, true, false, true. And P implies not Q is going to be true implies false is false. True implies true is true. False implies anything is true. Not P is false, false, true, true. So Q implies not P. Q, true, implies not P. False is false. False implies is true. True implies true is true. False implies true, again, true. So you notice that these are, in fact, logically equivalent to each other. They have exactly the same truth values all the way down the table. All right, we could also then add in some statement R that sort of makes sense for this. I have absolutely no idea what I would do, though. Let's see. R would be like... Forecast is correct. So forecast. Let's say that the forecast for this particular case is that we're going to get light dusting of snow. So, okay. Let's maybe check that real quick, because I think that might not really make sense. Okay, it snows implies that we have school and the forecast was incorrect. Okay, so actually let's go back on that one and say it's not a light dusting. We're going to get heavy. Forecast is for heavy snow. Uh-oh. I just froze. There we go. So let's check the statements here. So this is okay, the forecast is correct and it snows, which means that it's going to be heavy. Okay. Q and not R is we have school. This is not a real good argument, but we'll see what this comes out to be. All right, we have school and forecast is wrong, which seems to be at least something that makes sense. Okay, this one here is it snows if it snows. Then we have school and the forecast is wrong. Incorrect. Okay, so what does that say here? This says that if it snows, then we have school. Schule. This is not German, nor is Schule actually spelled that way, but whatever. It's cool. All right. If it snows, then we have school and parentheses here. Then we have school and the forecast is wrong. Or just incorrect. Or forecast is correct and it snows. Okay. So if it snows, then both we have school and the forecast is wrong. Or the forecast is correct and it snows. That's a weird implication, but it'd probably be better if we shifted some stuff around, but we'll just deal with it. So again, the only event in which this statement is false is when it snows. We don't have school. And forecast is incorrect. So when does that happen? All right, it snows, but the forecast is incorrect. So that's going to mean that we get light snow. But we don't end up having school anyway. So, right, and you can come up with any number of things. The heat doesn't work at school, so no matter what, if the heat doesn't work or the electricity or something, you're not having school, right? That is a law in the United States. If the building itself is out of commission, you are not allowed to be in it. Or there's light snow, but there's ice underneath it. And so you would be going to school, but we have this layer of ice which is making it too dangerous. So then maybe you don't have school that day. Or any number of other reasons you can come up with that you have a light snow, but you don't have school anyway. I know a couple of times the school districts around here have canceled school in preparation for a massive blizzard, and then it just missed us. So they're like, oh, guess it's a free day off that we have to make up in June. Right, so that is the only case, or those are the only cases, in which this statement that we had up above, if it snows, then we have school and the forecast is wrong, or the forecast is correct and it snows. Something to divert us anyway. All right. If there's anybody out there with any particular questions, let me know. Oops, I just screwed something up. No, okay. So let's go and check out the book. So we can get a few. Yeah, here we go. See if we can get some calculus going here. Okay. So if we get, let's do areas of regions in polar coordinates. Okay, so I can't remember how much of this we actually did last class, so we'll just do it all over again. It's fine. When we're looking at polar coordinates, we are looking specifically at what's going to happen in 2 dimensions with some concentric rings to talk about different r values, like r equals 1, r equals 2, r equals 3, etc. And then also what are all of these angles. So theta equals pi over 4 here. And if we want to get the area of a region in polar coordinates, then we're going to look at, again, let's just take some irregular shape that's just in the first quadrant. And if we want to find out what the area of this is, we're going to take a infinitesimally small shape like this, and realistically, again, it's infinitesimally small, not so humongous like this. We're going to take something like this, and we're going to say, okay, this could be approximated by an arc or a sector. And we want it to be infinitesimally small. Wow. So this infinitesimally small sector of a circle is going to have area equal to pi r squared times what proportion of the circle this is. Now, unfortunately, right, this theta here is going to be a d theta, and so it's basically 0. Hooray! Alright, so then what we can do at least is say, okay, let's pretend that this is theta out of 2 pi. And so our area here is going to be, we have a 1/2 pi's divide out, we have the theta r squared. But again, this isn't really theta, I shouldn't write that there. 1/2 r squared times theta, but again, this is going to be an infinitesimally small thing. So realistically, this is delta theta or d theta. I shouldn't write d theta really. It's not literally infinitesimal. And so what we want is then, again, the sum as I goes from 0 to infinity of 1/2 r sub I squared times d theta sub I. Now, most of the time, you're going to just say that d theta is going to be the same value as we keep going. It's not like it really matters because, again, we're going to be doing an infinite number of these things over this particular area. And so when we take this as the limit as, n, 0 to n, as n goes to infinity, now we get the integral as we go from, I shouldn't do a and b, theta 1 to theta 2 of 1/2 r squared, r being a function of theta, that'll be right, times d theta. Yeah, I don't necessarily like putting the square there, but anyway. So we can also rewrite it, theta 1 to theta 2, 1/2 block r of theta squared d theta. However you actually want to do that. So if we want the area inside the inner loop of r of theta is equal to 2 plus 3 cosine theta. One of the things that's going to go on here, right, 2 plus 3 cosine theta. If we have theta equals 0, we have cosine of 0 is 1, which makes it 2 plus 3, which is 5. So at theta equals 0, we have a value of r value of 5. All right, then at pi over 4, this is going to end up being root 2 over 2 times 3, so 3 root 2 over 2 plus 2. It's still kind of a big number, so we're out here anyway. At 60 degrees, we end up with a cosine value of a half. So this is 3 halves plus 2, which ends up with 3 and a half. It's like, I don't know, here-ish, somewhere in there. This is probably a bit lower, but still. Make the dots big enough no one will ever notice. When you have pi over 2, then the cosine is 0, so this whole term's eliminated. You're just left with 2. At 120 degrees, or 2 pi over 3, we end up with a negative 1/2 here. So this is a negative 3 halves plus 2 is going to be a positive 1/2. Gets really small like this. And then somewhere, right, the cosine value ends up being negative 2/3, and so it's exactly going to exactly knock this out. So we're going to want, when cosine of theta is I shouldn't do that. Right, let's start from the beginning here. We're going to say that 0, stop, 0 is equal to 2 plus 3 cosine theta, or then negative 2 equals 3 cosine theta, or negative 2/3 equals cosine theta, or theta, now I need theta, is equal to the inverse cosine of negative 2/3. All right, and this happens at 2 places. One is going to be the cosine, inverse cosine, arc cosine, of negative 2/3, and the other is going to be at 2 pi minus that. These are explementary angles. Practical upshot of all of this is that they are in 2 locations directly above one another. So we have a value here of inverse cosine of negative 2/3, which got arc cosine negative 2/3. Let's switch that to degrees just to think about it. This is going to be 131.81. Hey, the Taking Cup, how are you? And then if we do not 2 pi now, but 360 minus that answer, we get 228.2 degrees. So, again, this is about 131.8 degrees. This is about 228.2 degrees, give or take. How's math treating you? Okay, so theta 1 is going to be that one. That's our default. And theta 2 is going to be 228.2. It's our secondary answer. So basically what we've got is a big, well, it's not a circle, but a big thing that looks like this. All right, and then after this particular point, after 131.8 degrees, we end up seeing that this is going to go into the negative region. And so all these values here between 131.8 degrees and 180 degrees, or between inverse cosine of negative 2/3 and pi, we end up with negative values, which means that all this stuff is going to be thrown into the fourth quadrant here. So we get this, right? And then here at pi, cosine of pi is -1, and so we get 2 minus 3. So that's going to be a -1 here. That's really too far, but it's cool. We'll go like that. How do you think you did? And I guess, what was it on? Because some of that stuff can be kind of interesting. Then this is going to loop back to the exact same spot and go down like this, eventually making its way out and making a loop all the way around. This is what is known as a limaçon. And it ends up having this behavior where it curls around on itself like this. Because it's a cosine, it's going to be in the horizontal direction that it does that. If it were a sine, then it goes up and down. And also, depending on what the plus or the minus or the size of these values out here are, you're going to get different stuff. Yeah, alrighty. Congratulations. Or, well, here's hoping. It's kind of important to eventually align your expectations of how you did with how you actually did. Slopes and scatter plots. All right. Is this like a section on statistics? Our Algebra 1 classes in the United States have some statistics type stuff in it. Say like, okay, what's the correlation coefficient, or like, you know, approximately. Here are some options. Right, like here's a bunch of data. Yep. Yeah, sorry, I forgot where you were exactly, but not super important. I mean, no offense, but I don't want you to give anything away. So here, like the line of best fit would end up looking something, roughly speaking, like this. And so yeah, our slope value is going to, at the very least, be positive. So it's going to be greater than 0, probably close to 1, and the correlation coefficient, so like R, would probably be somewhere around like 0.6, 0.7. Yeah, I like teaching that. It wasn't my favorite, but like we did all right. Nope, nope, nope. Okay, that's nope. Okay. Oh man, it's close enough. Stop messing with it. I'm glad you found it easy. And if you have any questions on other stuff, let me know. Or if you just want to chat about mathy type stuff or anything else. So for this, yeah. So for this, because we're doing like the inside of this Limassol loop here, we've got kind of two options to go. We could go literally from theta 1 to theta 2, or because it is symmetric, we can apply that particular help and go from theta 1 up to pi. So somewhere around 132 degrees up to 180 degrees. And then we say this is going to be 2 plus 3 cosine theta parentheses, all squared, times a half, times d theta. Option 7. Alright, so this is 4 plus 6 doubled is going to be 12 cosine theta plus 9 cosine squared theta d theta. As we take the integrals of these things, the first two are super easy, you know, if you know calculus. So you get a 1/2 multiplied by, here we get 4 theta plus integrate a cosine, you get a sine back, so that's 12 sine theta. This is all evaluated from theta 1 to pi, and then we have a plus integral of theta, integral from theta 1 to pi, times, let's do the 9 out front. The cosine squared is not going to be nicely integrated, so here we have to do a power reduction formula, which says that cosine squared of theta is going to be equal to 1 plus cosine of 2 theta. Oh man. All divided by 2. See, I know the double angle formula, I just never remember the power reduction. I just remember the double angle formula. Start from here and then get this other stuff. Alright. So that's a half. Plus a half cosine of 2 theta. So actually, let's just bring that in. Right, so take a half is going to be 2 theta. Plus a half of that is going to be 6 sine of theta. Again, evaluated from theta 1 to pi. Oops. Right, we're going to want twice that. Because again, we're leveraging symmetry. This is only accounting for half of it. So then we need to account for the other half by multiplying by 2. It kind of depends on what shape it is. If it's spherical or approximately spherical, then the surface area is not too bad. Well, maybe I'll let you research it. It's not that hard, right? You just look up surface area. If it ends up being something that is not spherical, though, so if the ladle itself were slightly elongated in one of its dimensions, then it becomes what's called an ellipsoid. So you'd end up with something it's like not quite a sphere. So you'd have something that has a longer, it's called the semi-major axis. So, semi-major axis usually is like A. Semi-minor axis is usually B. And that's if we just look at it like on a one or two-dimensional plane. If we have to expand it into 3 dimensions, this becomes interesting because then we also have to take into account C. I don't even know what that would be called because you've got a major and a minor. The one in between, mezzo? Semi-mezzo axis? I have no idea. But anyway, yeah, so you've got 3 dimensions. Now you have to calculate an ellipsoid in 3 separate dimensions. You could find the volume easily enough doing calculus. The surface area you could also do using calculus, but I mean, for you it's a little not nice. The good news is that like all this calculus stuff, because it's a symmetric shape, the calculus just works itself out and ends up not needing to be a thing. So alright, so a sphere has a volume of 4/3 pi r cubed. Surface area is equal to 4 pi r squared. And then if we only want half, because it's a ladle, you'd have to know the equation of the dent or what shape the dent was in. If it itself is spherical, you'd need to know what the radius of the dent would be. So like if it's a spherical dent, that's super easy, except if it's like only a little piece, if it's like an arc like this out of a sphere, but your ladle only is like that big, you know, the rest of it curves out to here, and the dent curves out to here. Now you'd need to know, well, the radius of the dent goes all the way out into space somewhere. So you'd say, okay, my radius of the dent needs to be like this big, and the ladle is only about that big. So then you'd say, okay, how much does that take out? Well, it'll be this angle, whatever that is, over this sector taken out of the ladle. So it would be challenging, but not... I don't think it would be particularly... It could be difficult. Let's put it that way. So this is sort of akin to how Eratosthenes in the some number of thousands BCE. Let's look. Yeah, okay. So 200s BCE. So this is roughly 2,200 years ago. How he figured out that the Earth was round, and based on that, what the radius of it would be. Eratosthenes was only about 2% off. So it's pretty good for a 2,200-year-old calculation. Okay. So if you had a known distance like along the arc, so if you knew that this thing had a dent like that. And let's just zoom in on that for a second here. So if you knew that this had a dent that was this shape, okay, you could approximate this as a circle and say, okay, I think this is probably circular-ish, right? If it's like a weird dent, then, or like if it's sharper or something like that, it's not really going to work. But if it's round-ish, like you bonked it against something else that was kind of round, then one of the things that you can do is, again, approximate this kind of as a circle and say, all right, this kind of goes this way, and this kind of goes this way. So we could assume that the center of the circle is like out in space here. You'd know that this length, S, is going to be an arc. And then you'd say, okay, if I know that, I could also figure out, well, Eratosthenes had the sun, so that was a little easier. So we had like an angle theta here. So one of the other things that you should eventually know about circles is that as you draw the circles around, they have what are called tangents, which are at right angles to the curve. So we could end up having these tangents here, and they're at right angles to both the circle and the radius going to the center. So if you could figure out what the theta is here, that might be a bit challenging. All right, so then this would say that our proportion of S to the entire circumference of the circle. So let's back that up and say entire circumference of the circle. Take this and go all the way around like this. Would be equal to the angle proportion. So S is to theta as C, the circumference of the circle, is to 2 pi. You could also do 360 degrees. That's fine too. Yeah, you probably should do 360 degrees. Oh. Yes. unless it's a regular shape, right? Like if it's a cube. If the dent were almost perfectly in the shape of a cube, right? If it were smacked on the corner of the counter and you got a nice sharp dent to it, that would be really easy to calculate. But then again, if it's a partial cube, that's going to be a problem. So that's one of the problems. That's really one of the problems with all of this stuff is that, like, if it's a partial shape, it's going to be really hard to get the partial shape compared to, like, getting a full shape into something. Right, like, if we ended up... if we ended up doing something like this, you could approximate this as like a triangle. Say that, yeah, that's pretty close. Right? You say that, okay, this is going to be a triangle, and then the surface area of that thing you could physically get like a string or something and like measure out what the dimensions are along these two corners, and then you'd be able to say, okay, well, if this is, you know, side 1 and side 2, then it's just going to be like side 1, side 2. That's nice and easy. If you have to do this in 3 dimensions, this is going to get you like probably a prism. Yep. This will get you a prism. And so if that were like knocked in here, you'd be able to calculate, again, this should be like side 1, side 2, and direct distance. You could just measure that with a tape measure, like I said. And then this distance here would have to be depth. Ugh. That'd be awful. No, well, wait. This is depth because we're... width, I guess? So then, like, you've got areas of all these different shapes. So your rectangles around all 3 sides of the triangle, or the triangular prism, are going to be fairly easy to get. It's like S1W plus S2W plus DW plus, and then you'd have to get the area of the triangle times 2. Yeah. The area of the triangle, it depends if it's at right angles or if it's not. If it's not at a right angle, then you got to measure the height of the triangle. And that'd be a bit challenging. Surface area of the whole thing. Yeah, so this could be fun, but at the same time, it could be a lot of trouble. Because then again, if you're doing that, right? Well, you know what the radius of the sphere is. The problem is that you'd have to do like... Oh, that'd be interesting. Because you have a... You have a sphere. You'd be saying, okay, I want a cap. I want a circular cap, or a spherical cap, which is then going to tell us how large what is this angle? But it's not just in 2 dimensions, it's now in 3 dimensions. So it's like the angle that the cone opens up to, and then it has a cap for an end as well. So if you wanted to find the surface area of the cap itself, it's probably not as hard as I'm making it out to be, but say like this is going to be the proportion of theta to 360, but then I think you'd have to square that. And then you have to multiply your surface area of the sphere by this amount. I think that would do it. So the reason I say this is because if you're just doing like the length over here, right, the proportion that you get for just a length is going to be theta over 360 degrees. But then when you do this in 2 dimensions, so now we're talking like an area, then the area ends up getting scaled. All right, so let's show this, right? So when I draw one of these tiny little squares that I have on my graph paper, I get a 1 by 1 area. And then if I double it, right, double the side length specifically, right, now I get a 2 by 2 area, but I'm multiplying by 4 to get from the lower one to the higher one. Because again, the area here is going to be 2 by 2 entirely. Okay. Give me 1 minute. Be right back. Okay. Yeah. So anyway, the factors in the area equations take our length, and then we're multiplying by that same value in 2 dimensions. So both the length and the width, or the length and the height, would be multiplied by 2. So then that causes it to quadruple to get to the area. Now, if we want the volume of something, this is what gets really fun, is like, okay, you got a 1 by 1 by 1 cube. Again, I should zoom in on this. If I got a 1 by 1 by 1 cube, no problem. And I multiply all the lengths by 2, then I end up with a 2 by 2 by 2 cube. Well, what does that do? If that's 2 by 2 by 2, then the volume of this thing is going to get cubed. So it's going to be 2 by 2 by 2 compared to 1 by 1 by 1, which is just 1. So if we increase our lengths by some factor, then the length is just going to increase by that factor. The area is going to increase by the square of that factor. And the volume is going to increase by the cube of that factor. So here, I think the scale proportion for the angle is going to be decreased by scale factor for that angle and specifically for the surface area of the sphere will be decreased by multiplying by the square of this proportion, or ratio. Square of this ratio. Theta over 360 degrees. I think that's going to be it. We could pretty easily check this by just doing like literally 180 degrees. Do a semicircle. So that's awful. Okay. So if we did this, radius is just going to be 1, and then if we want to compare that to the surface area of the whole sphere, right, that's going to be 4 pi r squared is just going to be 1. So 4 pi is going to be the whole sphere. And then here, for theta equals 180 degrees, this should be... No problem. All right, have a good night. Thanks for stopping in, and hope to see you later. Might as well finish it. Oh yeah, no problem. So yeah, on next Wednesday, I'm gonna be a lot freer, so I might end up doing a few more streams, just randomly during the week. All depends on when grades are done and all that. So good luck. See you later. All right. Anyway, so if theta is 180 degrees, we're doing a semicircle, and so the surface area of this should be 180 degrees over 360. Oh, no. Nope, that's not working. Because we're taking literally half the... Oh, wait, no. Because we're not decreasing the whole sphere. That's the problem. Okay. Okay, so we take like 360, and then we have it doing that. We end up with a half circle, or half sphere, like a hemisphere. Oh man. And we still only end up with half the area. So when the angle is halved, the area is still halved. But it's a cap. It's not a wedge. It's a cap. Oh, no. Oh, man. All right, so if we do this as, here's a semicircle, we're going to cut it at some angle. Theta. Theta to pi minus theta. That's how we're going to do that. How do we get the area of this thing up here? So that's going to be a... Okay. Could do this. squared minus x squared, where x is going to go from like a negative x1 to positive x1. Get the circle. We want the rectangular area under the circle, but we're going to subtract off then the value here, whatever this y value is. It's going to be r sine theta, which is the same as y. So x in here could be r cosine theta. Oh, no. Wait, no, it's squared. It's squared. We're okay. Square root of sine squared theta. Alright, that's a little bit easier. Minus r sine theta. Minus r sine theta. Okay. It's not helpful. Because it's not always... Okay. Because it's not changing with this, right? So a constant value... You need to get a constant value out of a polar equation. So if it's like y equals... 1. This is r sine theta equals 1. So now r is equal to the cosecant of theta. Okay. That gets us a flat line. This is no longer going to be negative x to x. It's going to be as theta goes from theta 1 to pi minus that. This is going to be r times the sine of theta. Sine of theta has to be positive. It's going to stay positive in this particular setup, so cool. If it's anywhere else on the sphere, you can just turn it until it is always positive. So r sine theta minus cosecant theta. Theta goes from theta 1 to pi minus theta 1. d theta. Alright, that r is a constant, so we don't have to worry about that being a variable. Oh, gross. Integral of a cosecant is going to be a cosecant natural log of an absolute value of cosecant cotangent or something like that. Yeah. Man. theta plus cotangent theta. Yeah. This is going to be r cosine pi minus theta 1 plus natural log absolute value cosecant of pi minus theta 1 plus cotangent pi minus theta 1. That's going to be a negative here. Okay, and then this is going to be plus r cosine theta 1 minus natural log absolute value cosecant theta 1 plus cotangent theta 1. Okay. Alright, a cosine of pi minus theta 1 is going to be the opposite of cosine of theta 1. Just cosine of theta 1. So if we have these two angles here, their cosines are opposite values, the x values. So this is going to be r cosine theta 1, just the same. This is going to be plus natural log absolute value. Cosecant of pi minus theta 1 is going to be the same as the cosecant of theta. Plus cotangent of pi minus theta 1. We're going to get the opposite slope. Yeah, slopes are going to be opposite each other. So this is going to be the negative. Really? Alright. Of just theta 1. Plus r cosine theta 1 minus natural log absolute value cosecant theta 1 plus cotangent theta 1. So these two things are in a proportion now. These are in a ratio. These two can be added together. This is going to be 2r cosine theta 1 plus natural log of absolute value of cosecant theta 1 minus cotangent theta 1 divided by cosecant theta 1 plus cotangent theta 1. There's some completing the square, or not completing, difference of squares probably that I could manipulate this with to get something that's a little bit nicer to work with, but that's going to be cosecant squared minus cotangent squared, which might just be 1. That's nice. Probably. But then the top is going to be the square of that cosecant minus cotangent. Cosecant squared minus cotangent squared is going to be 1 again. So that's a 1 minus twice the cosecant cotangent. I don't think it's any better, but so if we do a circular cap, spherical. If we do a spherical cap, two-dimensional plane is going to be this. So how do we get it in 3? Just project it around. Yeah, do a revolution of solid. It's going to be... It's going to be a little different anyway, but it's not terrible. Anyway. Let's back out of this one. So we got a result. It's okay. Just being a little obsessive, it's fine. Okay, so going back to what we had before here, this is now going to be 1/2 times 9/2. That's going to be 9/4 theta. And here this is going to be 9/4 again. Cosine of, I'm sorry, if we take the integral, if we take the integral of this, the cosine becomes a sine, but the 9/4 that we get from the 1/2 outside, the 1/2 inside, and the 9 outside of the integral, and coupled with the fact that we need another 2 in order to get du for our function here, right? We got 2 theta, d theta. So then we need, if this is going to become u, we need u to be equal to 2 theta, and therefore du d theta, or du is equal to 2 d theta. So in order to get a 2 here to give it to the d theta, we need to get another 1/2 here. So that's going to be 1/8 times 9, or 9/8 sine of 2 theta. Evaluated from theta 1 to pi. All right, so 2 plus 9/4 is going to be 17/4 theta. Plus 6 sine theta plus 9/8 sine of 2 theta. So 17/4 pi plus 0 and 0, because sine of pi, sine of 2 pi are both 0. Okay, so that's going to just take that number, 17/4 pi, and then we're going to subtract 6 sine of theta 1, and also 9/8 sine of 2 theta 1. Really hope this works out. Alright, really? And then I forgot the 2 again. Ideally, I would have remembered here, and then not done all this other stuff. Alright, whatever. It's twice that. 17 halves pi minus 3 sine theta 1 minus 9/4 sine 2 theta 1. Alright, so actually, we need to find the sine of this particular value here, but we already know what the cosine is, so it's not actually too bad. So if the cosine is negative 2/3, and we're in quadrant 2, so we're saying that if we have quadrant 2 like this, a radius of 3, an x value of negative 2, what's the y value going to be for this particular angle? Again, keeping in mind that this is theta prime, and this is actually theta 1. Functionally equivalent, but still. So square is 9, square is 4. 9 minus 4 is going to be 5, and then take the square root. You get root 5 for this thing. So 17 halves pi minus 3 parentheses. What is the sine of theta 1? Sine of theta 1 is going to be root 5 over 3. Oh, nice. Divides out. So it's just minus root 5. Minus 9/4. The sine of 2 theta 1 is a little bit slightly more challenging, but all that is the sine of 2. Let's do alpha so we don't get it confused. It's going to be twice sine alpha cosine alpha. Okay, so this is going to be 9/4 times twice sine of the sine of this angle is root 5 over 3. And the cosine of this angle is going to be the negative 2/3 that we had to begin with. So 17 pi over 2 minus root 5. This is going to be plus. Okay, we got 2 and 2 makes 4, divided by 4. Those are all going to go away. We got 9, and interesting, a 3 and a 3 in the bottom is 9, so those go away. So we're just left with root 5. Which subtract out. Okay. So here we just get 17 over 2 times pi. So we should be able to get the same answer in our should be able to get the same thing in polar form. So if we go to r equals 2 plus 3 cosine theta, graph it, and then do a calc. That's not going to let us do it. Hooray! Curses. a little curious. If r is equal to 2 plus 3 cosine theta, then r is equal to the square root of x squared plus y squared. It's equal to 2 plus 3. Cosine is going to be x over r, which is the square root of x squared plus y squared. If we take that and multiply through, we get x squared plus y squared is equal to twice the square root of x squared plus y squared plus 3x. I mean, there's no nice way to solve for y, really, but why not try? So this is going to be x to the fourth plus y to the fourth plus 9x squared. You guessed it, Superbrain. X squared plus 4y squared. Filtered down, we get 1, 1, 1, and then on this row we get 1, 2, 1, 2, 1. So we get plus twice x squared y squared directly, twice x to the third times negative 3. So let's back that up. Right, twice negative 3 x to the third once they're combined. And on the other side, we've got wrap around the 9x squared. So we're going to get negative 3x times x here, so it's times the y. Alright, so twice y squared negative 3x. Okay. Minus 4x squared oops, right, the negative, or the 9x squared here is going to combine with the negative 4, so we get negative 13. squared minus 6 x cubed minus 6 x y squared should equal 0. So that's the equation of the limosol, I think. This one here. That's not nice. Yeah, so I don't think we're going to solve for anything here. As if that wasn't apparent enough. Alright, so we got y to the 4th plus parentheses 2x squared minus 6x minus 4 all times y squared. X cubed minus 13x squared. So if that's our constant, right, then this is not going to be just the cube of this thing. That's too bad. Would have been really nice. Equal to 0. Bah humbug. All right. So y squared is equal to the quadratic given with a equals 1, b equals this expression of x, and c equals this expression of x. That's y squared. So negative 2x squared plus 6x plus 4. Plus or minus square root. We only want the positive branch, so we can just eliminate the negative one. Alright, b squared. So 2x squared minus 6x minus 4, parentheses squared. Minus 4 times 1 times this whole thing. X to the 4th minus 6x cubed minus 13 squared. All divided by 2a. A is 1. So this is all getting divided. And this is going to have a, this is going to have a factor of 4 to take out from everything. So the 2 here is going to go away. That's kind of nice. And then we get y is equal to the square root of all of that. So this is going to be negative x squared plus 3x. Oops. Negative x squared minus 3. Nope. I didn't need to do that. Just draw an extra line. All right, plus 3x plus 2 plus 1/2 times a huge square root. It's not huge. The one on the inside. The nested square root. That's why it's really nasty. It's just because it's nested. Alright, so we're going to take a 4 out. This leaves behind x squared minus 3x minus 2 parentheses squared. Opposite signs is not going to get us 3. Okay. So it's x to the 4th. 9x squared. 4. So twice this thing is going to be a negative 6x cubed. And twice this thing is negative 4x squared. And this thing is going to be a twice positive 6 is 12x. X to the 4th minus 6x cubed plus 5x squared plus 12x plus 4. Alright, x to the 4th is 6x cubed plus 5x squared plus 12x plus 4 minus x to the 4th plus 6x cubed, maybe nice, plus 13x squared. Alright, the 1/2 already came in, so we don't have any divided by here. So y equals big square root negative x squared plus 3x plus 2 plus 1/2. This 4 is going to get square rooted and come out, combine with the half to just become 1. And then that's going to be multiplied by the square root of x to the 4th minus x to the 4th is gone. Negative 6x cubed and positive 6x cubed is gone. 5x squared and a positive 13x squared is 18 x squared plus 12x plus 4. So 9x squared plus 6x plus 2. If we factor out a 2 from all this stuff, we can factor that out entirely. This is 18. Do we get 6? 118, 29, 7, 3, 6. Huh. Okay. So that's not going to factor any nicer. This should be our y then, for the limaçon that we were looking at before. So now I'm kind of curious if I can do this just in function mode. Alright, so let's try this. We got square root of negative x squared plus 3x plus 2 plus 0.5 square root of, nope, not 0.5. I'm reading the wrong line. Negative x squared plus 3x plus 2 plus the square root of 18x squared plus 12x plus 4. Graph. Well, that's interesting. We get something that looks like this, which is not at all like the Limassol. So I think the problem there is that it is unraveled. It might be equivalent, but because it's unraveled from being this loop, it's now like this weird shape to it. Well, anyway. I'm gonna go grab my Advent calendar beer and head over to Jason Charles Miller's and listen to some Miller's Chillers music. So, thank you everybody for coming. We are... Oh no, is he done? Oh no! Yeah, I think he's done for the night. If he was on. Huh. Yeah, I was on 2 nights ago. He might not be on tonight. Okay. Well, that's what happens when I'm not kept up to speed on, or when I don't get up to speed on these things. So I think... Whomps do I want to raid? You know what? Let's go over and see SDK Phoenix. SDK is a great guy. He had I found him through Astroneer speedrunning. Captain Space Toaster had him as his raid target on several occasions. He's a nice guy, like him, and we're gonna raid on over. There's only 2 of us today, but it's fine. 2 of us, being me, myself, and I. But it's cool. If anybody else is here, you know, apologies for skipping over you. I only see 2 on my phone, so... Or, sorry, I see 1 on my phone, and it's myself. So, alright. Everybody have a good night. I'll see you on Friday for gaming if I am done with my grades. And if I'm not done with my grades, I'll probably still need at least a small break, and we'll figure something out. And again, like I said, next week I'm going to be probably streaming a lot more. We'll see how it goes. And I have a project during the regular day to work on some stuff with a friend